Hey, this is Dr. Thomas C. from Lockheed Martin in Littleton, Colorado. And there's energy in the air. It's T-1, just about 24 hours before this live broadcast starts of the tag event, the high five of OSIRIS-REx with Bennu.
And I'm Dr. Lori Glaze. I'm the director of the Planetary Science Division at NASA headquarters, and we are really looking forward to this big event.
And we're sitting here with a virtual NASA social, and we're answering questions that you submit with hashtag to Bennu and back. And we're going to start asking and actually answering questions. And the first question we already received is from Stephen Martin. What delay will there be in the signal, Lori?
That's a perfect question. There's actually going to be about 18 and a half minutes of delay. The Asteroid Bennu and the OSIRIS-REx spacecraft are about 200 million miles away from Earth, and so it takes about 18 and a half minutes for that signal to travel all the way back to Earth. So when we say that the tag event is going to happen at 6:12 p.m. tomorrow on Eastern Time, that's the time we actually receive that signal back. So the tag will have happened about 18 and a half minutes before that, but we'll get the information back here at 6:12 p.m. telling us that the tag was successful.
I just want to say, Lori, this is, we learn in school how the speed of light is what it is. It's like most of our lives, the speed of light is so fast, it never matters. Well, it really matters. Yeah, the speed of light feels really slowly if you get, this kind of activity done. We cannot joystick this. It has to be done autonomously. But here's the next question by Norman Gregory Fernandez. Do you have on-board spectrometers so you can at least get the chemical makeup of the object prior to sample returning, Lori?
That's a really, really good question. So the whole point of the sample return is to get those samples back here on Earth so we can really analyze them in detail. But before that, we've spent the last almost 2 years orbiting Bennu with the OSIRIS-REx spacecraft, mapping out the surface. And yes, we do carry a couple of spectrometers, an IR spectrometer, an infrared spectrometer, and an X-ray spectrometer. And those really help us to learn about the composition and what the makeup is of those rocks on the surface of Bennu. In fact, we found out some really interesting information from those spectrometers. We already thought that Bennu had a lot of carbon there on the surface, and we've confirmed that yes, there are these carbon-bearing minerals, organic molecules that are possibly the seeds for life, and we've been able to identify those with the instruments on board OSIRIS-REx.
I just want to add, the other thing that I was found out with the same instruments is actually kind of what they call radiation age of a surface. So we look at the body and realize actually the Nightingale crater is a really recent crater. So it looks really fresh. When the surface gets irradiated by the solar wind and the energetic particles that are out there in space, that surface changes, and so that the spectrometers are good enough to actually not even guess what the composition is overall, but even assess what the age is. And so for me, that's just, so we're prepared. We're going to go into kind of a recently excavated crater, so to say, just even hundreds of thousands of years. It's very, very young as compared to the age of course, the Earth and the solar system. So yeah, these instruments are really critical.
Yeah, and it's just amazing to me that we can, using our instruments remotely, not even touching the surface yet, we can already tell, generally just how old that surface is. Just incredible.
All right, so let's go to Brian on Twitter, who asks, does the head act as a vacuum and suck up samples, or is there any drilling that happens, Lori?
That is an outstanding question. This is a really clever device that was developed here at Lockheed Martin in Littleton, Colorado. They developed this really basic, simple head on this arm that acts like kind of a reverse vacuum cleaner. It's actually really very basic with no really moving parts and very simple kind of design. So that as the touch and go head touches the surface of Bennu, they're going to fire off a nitrogen canister that blows nitrogen through, and then it acts like a reverse vacuum. So that it puts pressure inside the head, and then of course there's no pressure outside. It's a vacuum, and it wants to suck that nitrogen out. And as it sucks the nitrogen out through this air filter, it'll pull in those particles and deposit them inside that filter so that we can capture them and bring them back.
Great explanation. So let's go to Ethan on Twitter, who asks, would landing on the asteroid change the asteroid's trajectory?
That's a really interesting question, and something that we think about a lot, because as we think about maybe to potentially someday trying to move an asteroid or adjust its orbit, we want to understand those kinds of things, of course. But in this particular case, Bennu is so big. It is, it's really quite a large asteroid. It's about 500 meters across. So think about 5 football fields across. And the spacecraft is really fairly small compared to that. The spacecraft is about the size of a 15-passenger van. And so as it touches the surface of Bennu, it's really only going to kiss it for just a couple of seconds and then back away. And so just that combination of the very, very small mass of the spacecraft relative to the asteroid and the fact that it really only touches it just for a very, very short time, it's going to have no impact on the trajectory of the asteroid.
So it's a really interesting question, right? Because it's both about the fundamental physics, and it's also about, is it important what's happening? So the answer is, of course, it will change. Mm-hmm. But it's such a tiny, tiny, tiny little bit that really it doesn't matter. There's so many other things that are much more important. For example, the big rocks in the asteroid belt that are flying by, some of them we don't even know how heavy they really are. They're actually rattling on this Bennu, on this asteroid, a lot more than this particular landing would, right? So just it's kind of how physics work, right? Yes, of course it does, but it's a tiny little bit. It really doesn't matter as compared to all the other forces that are there. Talking about forces, here is a question by Cupstar on Twitter, who asks, what's the gravitational pull of such a small object spinning through space?
Wow, that's a really, really good question. And I don't know that I know the exact gravitational pull, but it is really, really small. Compared to even the moon or other small bodies in the solar system, the gravitational pull is really, really low. And so trying to navigate our spacecraft around this asteroid has really been a challenge because it's every little move it's very sensitive to that. It's a very, very small amount. I'm sorry, I don't know the exact amount. I have to go look that up. It's a great question.
All right, Upstart, here's a commitment to you. We're going to give you on my Twitter account, which is Dr. Thomas C., we're going to give you the exact answer to that. But here's what actually is important, and you didn't put it in your question. It actually turns out it really matters where you are to assess that gravitational pull because of the fact that the object is so small. Remember, it's big. It's as big as the Empire State Building, in height, and even a little bit bigger around the midsection, so to say. Because of that, if you're right on the surface, you have a given gravitational pull, which is the number we're going to post. But if you're farther back and you're coming in orbit, you're farther back from that. The gravitational pull goes down the force with 1 over the distance squared or so of the body. So in other words, you go twice the distance, it goes down to a fourth, to 25% of the force. So it's a tiny little force. It's breaking all the records. We've never been in orbit around a smaller object. But the answer, to give the answer, we're just going to assume one distance just so we can answer it with one number as opposed to something bigger. I hope that helps Cupstar, and I'm really glad for the question. And here's Ray on Twitter who asks, I want to know the process of how one determines something is 4.5 billion years old. Yeah, so pick up the rock, Lori, and say, how old is that one? How do you know something is really, really old?
That's a really good question, and there's a couple of different techniques that are used. But one of the things that we can do is take some elements that are present in some of these rocks actually are radioactive, and then they decay over time, and they change from one type of element to another type of element as they decay over time. And by looking at the ratios of these various different elements, it gives us a sense of just how much time that particular, the first element was there and how long it's had that time to decay. And that's how we get a sense of just how old some of these rocks are.
That's a really, really good answers. You know, what's really amazing, if you look at nature, there's all these clocks around, right? If you look at the tree trunk, you see these kind of yearly kind of rings, which come from slower and faster growth, depending on what temperature it is, you know, especially if there's strong seasons that become even more distinct. At the very larger scale, you see the universe, which is expanding, which gives another time scale. And then in the middle are these kind of clocks, these atomic clocks that really are going down. That's also how we're kind of assessing, for example, how, you know, if you look at the outer atmosphere, a given element of our atmosphere, how long is it there? We can measure it by using the same kind of clock. So it's just a really cool way of doing that. So it's a whole bunch of clocks, and depending on what the question is you're using, you need to take the right clock. And now this was some of my favorite questions come from elementary school students from Virginia who would like to know, Lori, why is the NASA OSIRIS-REx mission to Asteroid Bennu important? Why is that important?
That is such a good question. And there are lots of reasons why this mission is so important. So I'll try to touch on some of these. One of the first reasons is that the asteroids that are out there in space, in the solar system, are these remnants. They're left over from when the solar system formed 4.5 billion years ago. And so by looking at the asteroids and studying them, we can learn and start to understand what that material was that turned into and made our planets. And so that's really, really important and fundamental to understand what that material was. Another thing that's really important about this mission is I talked a little bit about the carbon molecules and the organic molecules that are present and the minerals that might have water tied up in those minerals. Asteroids are one way that those organic molecules and water molecules get delivered to Earth. When asteroids come in through our atmosphere and they impact on Earth, they bring water and organic molecules, and those could be the things that started life, you know, some time ago. And we want to understand what those building blocks look like and how they got to Earth and how they might be distributed in other places and how does life actually form. So that's a second really important reason. A third really important reason is that sometimes these asteroids can be dangerous to us here on Earth. Sometimes they can come and intersect with our orbit around the sun at the same time we're there, and if that happens, if they're big enough, that could be a problem. It can cause a lot of damage. And so we want to really understand these asteroids. We want to understand how they're held together, what kind of materials they're made out of, what their trajectories are, meaning how do they orbit around the sun, so we can very precisely predict when and if they might intersect with Earth and impact Earth to help us better be prepared when that happens.
Love that answer. I mean, for me, one of the things I learned from early results from this mission is how the actual analysis of the asteroid itself really helps us understand how radiation shapes the orbit of this particular object and therefore of others. So it really helps predict, you know. And if one of those bodies came hurling towards the Earth, it would give us a much better way of actually warning people and move out of the way. It really protect life, you know, for those kind of events that happen, unfortunately, from time to time.
Yeah, and in addition to helping us prepare so we can get out of the way, which is very important, if we know about them soon enough, if we have a long enough warning, we might even be able to send another spacecraft out that could make small, tiny adjustments in the orbit of the asteroid so that when it crossed Earth's path, we're not there. And so that would help keep us safe as well. So there's a variety of things we can do.
Have you ever done this, bumped a little body? Are you going to do that?
I'm so glad you asked. In fact, we're in the process right now of building a mission that's going to be the first ever test of how we can move or gently bump or nudge an asteroid out of the way. We actually have a mission called Double Asteroid Redirection Test. that's going to launch next summer in 2021, and it's going to intersect with another asteroid called Didymos. And we're going to run the spacecraft right into its little small moon and hopefully change its orbit. We can test that technique and see just how well it works.
All right, so why is it important? Number one, it tells us about the history of the solar system. Number two, it gives us important information about the history of life itself. And number three, it's useful because it helps us get better warning for objects that may hurt us on Earth and in fact, even potentially help us bump those out of the way based on the information we have.
Exactly.
So here is a question from Cosmariosities. Wow, that's the most amazing name ever on Twitter. Cosmariosities. Scientists say that samples OSIRIS-REx will collect will be very important because they will reveal us a lot about information about our solar system. But how will they do it? Can actually 60 grams of rock and dust give us that much information?
Yes, so 60 grams doesn't sound like very much. In fact, I think if I remember correctly, it's about 2 ounces. It's about, if you were holding a candy bar, it's about as heavy as a candy bar. So it doesn't seem like very much, but actually, this is going to be the biggest sample that we've collected in outer space, except for the Apollo samples where we had astronauts that picked up rocks on the surface of the moon. So this is going to actually be the biggest sample we've brought back since Apollo. And there is actually an incredible amount we can do, even with 60 grams. And in fact, even that 60 grams, we're going to put 3/4 of that, 75% of that sample, we're going to save it for people to use in the future. So this mission, we're just going to look at a small part, and we can look at little tiny grains, we can look at all aspects and very tiny bits of that sample. So it's really going to be amazing. We'll take those little samples and we'll look at them in our state-of-the-art instruments that are here on Earth, and we'll really be able to learn an incredible amount about what makes up those rocks on Bennu.
We had a mission called Stardust quite a while ago, and they brought back tiny little grains from a comet. The first such grain samples to come back. And those tiny little grains, if you added them up, I don't know whether they were a single gram.
I don't think so.
But I have to tell you, there are many, many different publications that came from that. Mm-hmm. And one of the key reasons many people forget is the analysis techniques are so sophisticated. Our scientists can basically take the tiniest amount of data and answer the questions of the type that we talked about earlier, these compositional questions. And so if you look at this, take a few sugar packs, perhaps 30 sugar packs of material, there's a lot of samples there for many, many years to come. So we really look forward to that. There's another question, Lori. Since this is a sample return mission, are there any planetary protection measures that need to be put in place for this kind of mission? Do you mind first explaining what planetary protection is and then answering the question?
Sure, that's a really good question. So when we talk about planetary protection, this is an important topic, both scientifically and for people's health. When we send a mission, for example, when we go to Mars, we want to be very careful that we don't contaminate Mars with anything that came from Earth. So we want to protect that environment as well. And when we bring samples back from someplace like Bennu, we want to make sure that if there's something there that might make us sick, we want to make sure that we're protecting against that as well. But I'll say that on Bennu, we really don't expect there to be anything there that could be harmful. So the planetary protection requirements for an asteroid sample return are pretty minimal. The asteroid's been out there in the solar system, rotating around, orbiting around the sun for 4.5 billion years, subject to all the radiation from the sun and the solar wind. And if there were anything, these organic molecules are there, are not actual life. They're just building blocks. They're just the key elements that might, but we don't expect there to be anything that could actually live in that environment.
So it's really important to this answer, and of course you were implying it. We did think of this already, And we, based on everything we know from science, we made a decision on what we need to do. And in this case, there's really very little, no danger of any type that from that perspective.
Yeah, and I'll mention that, we get bits of asteroids coming onto Earth every day through meteorites that come through the atmosphere, and they also contain similar types of these organic molecules, and they aren't dangerous either.
Yeah, they have been with us and our parents and
Yes.
grandparents and so forth. Where in the solar system, Lori, is the asteroid?
So that's a really good question. Most of the asteroids that we think about in our solar system are in what we call the main belt of asteroids, which is between Mars and Jupiter. But Bennu is interesting because it's in kind of an unusual orbit that comes out and then comes in close to Earth. It's what we call a near-Earth object. And so it's in kind of an unusual orbit. It's going around the sun, but it's not trapped in that space between Mars and Jupiter. It periodically comes in. That's why we worry about potentially coming near Earth sometime. It's a near-Earth object, so that's where it is. And actually, right now, it's pretty far away. So if we're where we are on one side of the sun, it's almost all the way around on the other side of the sun.
That's right. So it's really far away. So
Yeah.
most of the time, Bennu is actually less than 18 and a half
Right.
minutes away from Earth because it's closer. But right now, it's really pretty much on the other side there. So that's great. So I'm going to combine two questions into one, and that is, how fast does OSIRIS-REx touch down, and or what is the maximum amount of time allotted for the spacecraft to remain at Bennu?
Okay, so how fast is it going when it touches down? And we were just talking about this with the team earlier today. The spacecraft actually is moving very, very slowly, and when they've got a couple of maneuvers they have to make to set it up so that it can come down and take the sample, and those are very, very microscopic, changing the velocity of just really by a fraction of a centimeter per second. And as the spacecraft comes down to take the sample, it's going to be moving on the order of about 10 centimeters per second as it comes in very, very slowly. It's going to touch the surface for a couple of seconds, and then it's going to start backing away again slowly.
And that's the trick we all learn once we learn how to drive cars. If you want to park into a tight spot, you go slowly, right? So we're trying to do that here as well. Very short time there, but really the roll up to it is hours, literally, of activity to make sure that everything goes exactly the right way. So here's a question for you. Are there any instruments or experiments that the team tried to fit in this project that ultimately had to drop, Lauren?
Oh, this is looking back. I'm sure that is true, because doing a mission of this size is really, really challenging. And it's critically important for the team to focus in on the science. We would love to send every instrument we could think of on a mission like this. But we do have to focus, and that generally means that something's not going to go. And I seem to recall there was something that got jumped, that had to be taken off of the mission as it was going through its original part of its competitive phase when it was being proposed. I don't remember exactly what instrument it was, but I know that there was one that came off as it was getting ready to go into its final selection.
So I have a story for you, Lori.
Okay.
I've never told you that Mike Drake was the first principal investigator, and unfortunately he's no longer with us. And he actually told me how he struggled to get all the science. We had a drink together after a meet, and he told me how hard it all fit. The answer to that question is always yes.
Yeah.
It's just the way it works. The answer to that question is always yes. We try to get the absolutely most important instruments. There would always be more instruments if we desire to do so. So I'm going to go to Masim's question on Twitter, who asked, do you think Bennu and Ryugu are of the same parent body? If so, why? Is it possible to find out when the parent body broke up, and how the material would have chemically evolved?
That's a really interesting question, because when you look at Ryugu and Bennu, if you didn't know the difference, they actually look really, really similar. They both have the same kind of shape. They've both got really blocky surfaces. But in fact, they are compositionally, they're very different. When we look at Bennu, we see rocks on the surface that have minerals that contain water. We know that there's water trapped in some of those minerals. We see these, the carbon compounds there. At Ryugu, what we think we saw is actually something that was much drier, that didn't necessarily have those water-based, as many of those water-based minerals. So they seem compositionally somewhat different. In this particular case, we don't think that they're genetically related, but we do look for those kinds of things. For lots of asteroids there are, you can tell that when they break up, they travel together, they continue moving together, and we can tell that they're from the same kind of family of asteroids that maybe of a parent that broke up. But we don't think Ryugu and Bennu were from the same family.
So before I ask you the last question, I just want to remind everybody that they can continue in the discussion with hashtag to Bennu and back. Of course, the tag is at 6:12 Eastern tomorrow, and the NASA TV starts the program at 5 o'clock Eastern to 6:30. And I was so excited for that. And here's the last question, which is, how long will it take for the samples to come back to Earth, Lori?
That's a great question. The big deal is tomorrow we're going to collect the sample, but then what's really important is when do we get to actually look at the samples? They are actually going to return to Earth in September of 2023, so about 3 years, a little less than 3 years. They'll be back on the surface of the Earth, and we'll be able to open up that capsule and start the analysis.
We look forward to that and, of course, to tomorrow. Thank you so much, all of you, for the questions, and continue interacting with us. Listen to this amazing broadcast in various ways, and especially tomorrow when we actually high-five Bennu with OSIRIS-REx. Thank you so much.